Okay, welcome to part 4 of the digital system design module of electrical and electronic equipment for industrial machinery experiment courses. In part 4, we will study about the sequential logic circuits. Previously speaking, we can say that previously we have the input, and this when we have the output, so the output related just the current input, but in the sequential logic circuits, the output is not affected by the current input, but it also affected by the previous output. So we have the two definition about latch and flip-flop, and previously speaking, we can say that latch it don't have the clock. We don't have the clock. We don't have the clock. And first we study about the SR latch, the state. So based on this is the symbol of the circuits here, and you can see that it include two NOR gate, right? Two NOR gate, right? So what is this circuit do? So here is the truth table of the circuit, and very interesting here is we have the future state and the current state. So what is it? So I will briefly explain it. Okay, so this is the SR latch, and example here in the previous state. In the previous example, I have the Q output is 0. The output is 0, and this one is 1. So now the current output is 0 and 0. So what will happen? Based on this circuit, we will know that the next output here also 0. So that means the path and the current are the same. So this one is this one. So that's this one. So it doesn't change the state when the output R becomes 0 and the S becomes 0. And the application of the SR latch is for the button. As you know that the mechanical button, they have a spring. So when you click the button, right? When you click the button, the spring will bounce, and when they bounce, they will have some voltage here, something like this, right? And then if we make a circuit with the SR latch here, the V value here will be stable. It will eliminate this situation. Okay, so it's also based on the truth table here, and this is another example. This is the input. We have two input. And this is the output. Of the SR latch, and this is the waveform of the S signal and R signal. So you have to roll the waveform. According to the input here. So this is your exercise, and I think that you can do at your home. And we have another thing we call this is the control. The control here is something like the don't care, like the don't care signal. Example here, you can see on the truth table here, you can see when C becomes 0, that the R signal and the X signal, they don't care. They just will keep the value, the bus value. They will keep the bus value. So whenever the C gate become 1, so the SR latch is active again, and it will up like the SR latch, similar the previous one. Okay, so here normally when you buy a chip outside, and you will have something like the control gauge here, the control gauge here. Okay, and this is also the exercise. This is also the exercise. I have the S and R and E here. E here is the enable. We call this is the control like the C gauge in the previous slide. And you also have to roll it. You have to also have to roll the remaining waveform of the Q. Okay, and this is also another example. And another very famous latch, we call it JK latch, and this is the symbol of the JK latch. And in this truth table there is something called toggle here. So that means when J equal 1, K equal 1, the state of the Q will be toggle. Example, in reverse state it becomes 0, J1, K1, and then Q become 1. And then if J1, K1 again, Q will become 0 again. So it becomes something like toggle. And J equal 0, K equal 0, Q will hold the past value. Okay. Okay, and another sequential logic circuits, we call it a flip-flop circuits. So the flip-flop circuits, so as I already said before, the flip-flop circuit, they will change the state of the Q value here based on the clock. And clock we call this is the CK here, and CK here this is active 1, and this here is active 0. So that means this one will active on the rising edge from low to high, and it will active or change the Q value when there are a falling edge here. That means from high value to low value. And we have the first one we call it a flip-flop, the flip-flop, and this one is the action table of the flip-flop here, and this one is the action table. Here you can see here, right, this will active when it's rising A, right, and this will active when falling H here. Okay, and here you can see here this when it's active, right, when D is 0, here the Q will 0, and when D is 1, Q is 1, right, Q is 1. Okay, so this is the waveform. You can follow it. Here. Example, this is the clock input into the flip-flop, right, and this is the state of D here. Okay, so when D equal to 1, right, so Q become 1 when it is active, right, right. And here example is similar, right, D is active, right. So when it's become low, right, if this is the latch, they will change the Q value, but here this is the flip-flop, they just active when on the rising edge, right. So from here to here is still high value, right. So that is the difference between the flip-flop and the latch. Okay, and this is the chip name outside, you can buy on the market. Okay, and this is the animation of the flip-flop. They change the flip-flop, they change the traffic light. Okay, and another thing is we have the JK flip-flop. Previous we have JK latch, right, and here we have JK flip-flop. So the action table is similar with GK last, but just the difference is the flip-flop, right? They must have the pawns here, they have to have the pawns here, right? And this is the example there, and this is the example of the GK flip-flop. The GK flip-flop example, this is the waveform of the J, like waveform of the K, right? And this is the clock, right? And trigger is negative, that means falling X, right? So you can see here, right? Based on the table, we will have the Q value here. We will have the Q value here.